This presentation is looking at the modelling of Soakaways within InfoWorks ICM or CS. So firstly, what is a Soakaway? Well, first what you need is a connection from a property roof. So literally just a pipe, generally in the back garden, which connects via a downpipe into a pipe that runs under the soil into what is literally a hole in the ground. So we dig a big hole about 1 metre square, 1 metre deep. Now it could be completely open. We then fill it with some sort of permeable gravel or something like that. And then we introduce the actual structure itself. Now this could be a crate, as we've shown here, with a very high porosity, or it could literally be an open tank. But the key thing is that it provides a large volume to store the water and some mechanism where that water can soak into the surrounding soil. So once it's been installed, it would then be covered. We can see the connection point there to the pipe from the property, and then it's filled over again with permeable material, and the garden or wherever it's installed would be returned to how it looked before. So when it comes to modelling these things, it's really very simple. We can see the incoming pipe there. Now the soakaway itself is represented as a node, and what we have the ability to do is to also represent a pass-forward pipe, which may connect this soakaway into the existing sewerage system. So it's really a very simple pipe, node, pipe arrangement. When we look at the characteristics of the node, the soakaway itself, it has all the familiar attributes. We defined its chamber size, its shaft area, that kind of thing. But we have an additional parameter here called Suds Parameters, where we are allowed to introduce a base area, a perimeter, an infiltration loss, and a porosity. Now the key thing here is that, for example, the base area has absolutely no relationship to the chamber area. The chamber area and the shaft area, they define the volume of this node, whereas the base area and the perimeter, all they do is they're used in the calculations of how much flow is lost from this node. So we take the base area of 2 meters squared, multiply it by the infiltration loss in millimeters per hour, and that gives us our total loss rate from the base of this structure. Similarly, if we know the water level in the node, we know the perimeter, so that gives us like an exposed side of this soakaway. Again, multiply that by the infiltration loss rate, and that gives us a loss rate through the sides of the soakaway. Porosity, we can see, for example, in this case, it's fairly high, 0.8. So that would mean that a depth of water in the soakaway would be increased slightly due to this porosity. That would then expose a greater depth, which would be multiplied by the perimeter and the infiltration loss coefficient to give us a loss from the sides. So the lower the porosity, the higher the rise is introduced from just the normal water that's in the soakaway itself. So what happens here is we've got a very short, intense rainfall event that we can see there. And this produces a level increase in the soakaway. And then gradually we can see over a number of hours after the storm is finished, the level gradually reduces and returns to the base layer. When we look at this in terms of infiltration loss, what we see is that because there's a depth of water in the soakaway, more of the sides have been exposed, and therefore we have a greater loss rate, which is a function of the level. So a very, very simple node structure. It's basically a leaky node. It allows us to lose water through its sides and its base, and that's really all there is to it.